5 class. Let us rewind the previous class sessions. Previous class session I explained about eddy current. Now in the eddy current some concept I missed here. So let us revise and explain about once again a small concept which is missed. I told you in the last class that when a metallic plate is led to oscillate between the magnetic field, its oscillation will get damped. That is, its oscillation will reduce. That's why it is called damping effect is there. Now when the metallic plate enters the field, when the metallic plate enters the field, you will see that there is an increase in magnetic flux. Due to this increase, there will be an induced EMF produced in the plate. Now we try to oppose the increase of magnetic flux and generate a circulating current. That circulating current is called as a eddy current in a bulk piece of conductor I told. Now here the direction of the current is observed by the Lenz's law or Fleming's right-hand rule. Now you see that there is an anti-clockwise direction. But I draw one more plate, which is a plate is leaving the magnetic field. I have not told you that. When a plate is leaving the magnetic field, the magnetic flux links with the plate will try to decrease its value to 0 once again. It means that the magnetic flux is decreasing now when the plate is leaving the field. Okay. Now in that case, what happens? Once again, induced EMF will be formed. Now this induced EMF will try to oppose the decrease of magnetic flux. Try to oppose the decrease of magnetic flux. Hence, what happens here? Once again, a current will be induced. Now, what is the direction of current? According to Lenz's law, the induced current try to oppose the decrease. Now, to oppose the decrease, what direction has to go? Definitely, it has to go in the direction of clockwise direction, so that it has to pull back to the same position. Now, it will be the circulating current induced when a plate is leaving the magnetic field is in a clockwise direction. Which direction? In a clockwise. Now what happens? The plate which is facing north side will acquire south side. The plate which is facing a north pole will be acquired. South pole is acquired north side. Please do remember. When the plate is entering the magnetic field, the flux increases. Due to this, an induced current is EMF. Induced current will be induces in a plate. Now direction of current will be, because the flux is increasing, the direction of current is anti-clockwise. Please do understand this very important word. Once a flux is increasing in a plate, in a conductor, the direction of current is always anti-clockwise direction. If the flux value decreases, then the direction of current in the coil or the plate will be in clockwise direction. Now this is a small concept which is left out. I explained today. Now the next concept I explained in the last class is that, which is the self-inductance. Self-inductance, I started about self-inductance. I told you what is the importance of what is about self-inductance. It is a property of a coil due to which what happens? It opposes the increase or decrease of current in a conductor, or called in a inductor. In the self-inductance what? It is a property of a coil or an inductor which opposes the increase or decrease. Sometimes some books refer the word growth or decay. Growth or decay of current in a inductor is called as self-inductance. Self-inductance. Okay, one more point is very important here. Sometimes because it opposes growth and also it opposes the decaying, that is the decreasing. That's why it is called as inertia of electricity. This is very important word for you. Self-induction or inductance is called inertia of electricity. This is very important concept for you, this particular word, inertia of electricity. Now this is a word coined for self-inductance. Why? Because it tries to oppose the growth of current in a inductor coil or a simply coil, or try to oppose the decrease of current. Try to oppose the decrease of current. Hence, as it is opposing, similarly as if you are studying in a mechanics at mass. Mass is an inertial factor. When it try to oppose the motion of an object, because whenever it try to, you studied about inertia of rest, inertia of motion. Now if I keep like this, it is trying to keep in a rest, that's why it is fallen. Now these things I very understand that the inertia of electricity is a self-inductance. Why? The question asks you have to tell that it is try to oppose the growth of current and try to oppose the decrease of current. As if like you are studied about inertia of motion or EMF steps, that when you are standing in a bus, suddenly bus starts, there is a jerk of your front body will move forward, or suddenly the lower part will get rest. That's why suddenly when the bus starts, inertia for rest, you have to go back, and suddenly bus stops, your body is in front, bottom half is stationary and the top half will be trying to in motion. That's why will go more. The same case, this is also, it will oppose the growth or decay of current in a coil. Okay, let us move on to the next concept, which is today's topic, which is now what I explained about self-inductance I explained. Now today's class explain the coefficient of self-inductance in a solenoid. This is a derivation you will ask before. Derived expression for coefficient of self-induction in a solenoid. Now let us derive this expression, because in the last part I derive the coefficient of self-induction in an inductorized. Now this is a particular things is given, that is, let us consider an inductor. Say a current I is flowing to the inductor. Now this inductor is having length L and cross-sectional area of this inductor is A. Is a cross-sectional area of the inductor, and here in this coil there are total n number of turns are there. This small n into L, what is the small n? The total number of turns per unit length, where n is the length of the coil. Now this n is total number of turns in an inductor. Now you already studied in the previous, that is magnetism matter topic, that the magnetic field developed when the current is flowing to the inductor coil, it is as if like A force solenoid it is. Now what is the magnetic field expression? The magnetic field expression when the current flowing to the solenoid is given by mu naught n into I. Mu naught n into I. This is the expression for magnetic field produced in an inductor. Now let us move on to the flux developed. The flux linked with the, this will be given by B into area, magnetic field into area. Now if there are n number of turns, what are right? The total flux links with this complete solenoid is given by NBA. Okay, n is what written? Number of turns per unit length into length of the solenoid. Now B is what? Magnetic field produced in the solenoid. Magnetic field produced in the solenoid is given by mu naught n into current flowing through it. Now A is area of the solenoid. Now according to the definition of magnetic flux, according to the definition of self-inductance, the magnetic flux is given by L into I. Now equate this equation number 1 and equation number 2. Add down to theoretical words and we have to write that according to the magnetic field produced in solenoid when a current I flow through is this. Now the magnetic flux links with the total solenoid will be, for n number of turns will be this. According to definition of self-inductance, the flux links with the L into I. Now comparing equation number 1 and 2. If you compare equation number 1 and 2, what happens? L into I is equals to n square, because here the n, that's why it becomes n square. L length mu naught A into I. Now here is I, here is I will get cancelled up. What is the meaning? L is equals to the self-inductance or coefficient of self-inductance in a solenoid. L is equals to n square L mu naught, see that, into A. Now this is the very important equation for you. Now you have to understand what is how to derive the expression for self-inductance in a solenoid. Self-inductance in a solenoid. Some of the words we have to write down. Please cope up with that. Consider recitation you have to write. Then magnetic field, flux. Now let us understand this. Derive the expression for self-inductance of a solenoid. Let us go to the next concept, which is energy stored in a solenoid or energy stored in a inductor. Energy stored in a inductor. Now please pause the video and record all these steps. This much only is there. Now you have to write down all the equations properly. Now in the board examination, in Karnataka board examinations, they will ask you how the self-inductance is related to number of turns per length. It is n square for 1 mark question. That's why I already told you that on what factor the self-inductance is dependent. The self-inductance is dependent on area of the coil, on the material on which the coil is wounded, or number of turns. Now these all things, there are 3 important factors I told you that self-inductance is dependent on it. Now, how much amount of energy stored? That is very important for us to understand. Energy stored in a inductor. Now this question will be asked for you for 3 marks. How much marks? Basically it is asked for you for board examinations for 3 marks question is there. Now this is very important question for 3 marks section. It is how much amount of derived expression for energy stored in inductor. Energy stored in inductor. Now let us consider once again an inductor where current I is flowing. The inductor is having length L, cross sectional area A. One more time we'll write down here. Here dq is a small charge on a coil. Once again, n is a total number of turns. Now, according to the flux linked with the inductor, what is the Faraday's law? The flux linked with the inductor is given by, according to Faraday's laws, will be the induced EMF in an inductor. The induced EMF in an inductor will be given as minus L into di by dt. Now what happens when current flows through an inductor? There will be an induced EMF. Now this induced EMF try to oppose this applying current. Now this is the induced EMF. Now if I want to push the charge in a conductor, I have to apply an external potential. I have to apply so that to whatever opposition offering from the inductor, I have to overcome that, and then I will push my charge in an inductor or through an inductor. That's why an external potential applied, it has to be opposite to that induced EMF. Now the external potential applied to drive the current. For what purpose are applying external potential? Because in inductor and induced EMF is generated. This induced EMF try to oppose your applied current. That's why I have to apply an external potential so that I have to overcome that opposition. That's why external potential is applied to drive the current in a inductor. Now that has to be opposite. That is E dash is equals to minus of the. Now what will be the external potential equation? Minus the minus what it indicates here? Minus just literally indicates an opposing factor. Now it is L di by dt. L di by. I hope that you understand this much now. Now if a small charge is there, dq is a small charge in this inductor at this point. dq is a small charge then work done by external potential, work done by external potential to drive this charge. This matter to understand. What happens? I am telling you that if dq is considered a small charge at this point, now how much work I have to do that this one simple small charge has to be pushed or it has to be driven in an inductor. How much amount of work I have to do it? Now that is according to work per energy, that is according to a definition of work, that is a small amount of work required to drive this charge will be external potential applied into your small charge. Now what is the expression for external potential? That is L di by dt into dq. Now if I rewrite the equation like this, L dq by dt into di. Now here as per the definition of current, dq by dt is what? Rate of change of flow of charges is called, rate of flow of charges is called as current. That's why L I di. Now this is what? This is a small amount of work done, or this is a work done for one single charge to drive from this point of the coil or inductor to this point. Okay, if there are many charges are there, I want to how much energy or how much work is required to drive all the charges, whatever available charges are there, to drive all the charges from this point to this point. What I have to do? How much amount of energy? Now I have to integrate this above equation for total current or to current to reach maximum value. When the current will reach maximum value, when all the charges are driven from this point to this point, this point to this point. Hence, to determine that, what I have to do? The current, the total work done required to reach the maximum current in an inductor is get by integrating this above equation, we get the total work done equation. Total work done equation for reaching maximum current. Reaching maximum current in an inductor. Now, total work done to reach maximum current. I say it is I0 is the maximum current. To reach the maximum current in an inductor. Now what I have to do? I have to integrate this equation. Here I have to do the current from 0 to maximum value, that is, I hope that is visible for you, I0 L into di. Now here L is a constant, it will not get integrated, it will come out. Now only what is varying with the time, that is I is varying. That's why the equation will come like this: L I limits condition. Now this will be of 1 by 2 will come. 1 by 2 L I0 square. Now this is what happened. This is the total work done. This is the total work as required to push all the charges or to drive all the charges from this point to this point and the initial point to the end point. Now this energy, this is what called external energy is there. Now whatever external energy I am applying, external potential energy I am applying, that has to be stored in the form of magnetic energy, energies. Now whatever amount of work I am doing here, this work to drive this to reach the maximum current in inductor, this work done will be stored in the form of magnetic potential energy in a inductor. Magnetic potential energy in inductor, and it is given by the total work done is actually L into I naught square. This total work energy will be stored in an inductor in the form of magnetic potential energy. Magnetic potential energy, that's why we indicated energy stored in inductor is half L I naught square. Now, what forms the energy stored in an inductor? In the form of magnetic energy. In the form of magnetic energy. The sometimes also called magnetic potential energy. Magnetic potential energy. Magnetic potential energy. Please remember this very important word. Now, this is the expression for energy stored in an inductor. Energy stored in an inductor. I hope that you all understand that. I will revise in quick manner. Now what I will, I consider an inductor. I wrote all this length, area, number of turns and small charges which are draining in an inductor. I wrote the, according to Faraday's law, the induced EMF in an inductor will be given by E is equal to minus L di by dt. Now, an external potential is applied to drive the current to an inductor, so that you have to overcome this induced EMF. Now that is the positive. Now this small amount of charge which has to, whatever amount of work is required to push this charge will be this one equation. Now I got this value for one single charge. Now total work done to reach the maximum current, that is integration method. If I integrate, I got this value. Now this work, whatever I done, that will be stored in the form of magnetic. When I do external work here to push the charges here. Now that external work is converted in the form of magnetic potential energy, or stored in the form of magnetic potential energies. Now this is the expression for it. Now the same case the question will be asked for you. What is the energy stored in a solenoid? What is the amount of energy stored in a solenoid? Now you have to write up to this much. When it is reached here, if the question is for 5 marks, if some of the question is asked for 5 marks, still one is not asked for you. It's only asked for you energy stored in an inductor for you. Now, if the question is asked for you for 1 mark, will ask for you write the expression for energy stored in a solenoid. Energy stored in a solenoid. In that case, what you have to do? You know the equation. Energy stored in vector is half L I naught square. Now, what is the magnetic field in solenoid? That is magnetic field in solenoid is mu naught. Okay, let us derive expression for energy stored in a solenoid. The energy stored in inductor expression is given by U is equal to half L I naught square. Whereas the magnetic field in an inductor is mu naught N into I naught. Therefore, ion equation will come out. I naught is equals to B divided by mu naught into N. Whereas last point I derived the expression for the self-inductance, coefficient of self-inductance in solenoid expression is given. L is equals to N square mu naught L into I. Now substitute this L and I naught value in this equation. You will get the energy stored in an inductor equation. Energy stored in inductor equation. Now let us substitute and derive expression for that. Energy stored half. What is this L value? L value is N square mu naught L into A. What is the L value? N square mu naught L into A. N square mu naught L into A. Now substitute the current value. Current value substitute what becomes? B square mu naught square into N square. Now N square will get cancelled here. 1 mu naught will cancel. What is the remaining? U is equal to half B square by mu naught into L into A. Now this is the energy stored equation in a solenoid. How much amount of energy is stored in a solenoid? Now the next concept we will go to, that is the magnetic energy density. Magnetic energy density in a solenoid. Magnetic energy density. Now usually that is represented by U bar. The magnetic energy density is how we write? U bar is energy stored per unit value. Energy stored per unit value. Now value how we write? Length into area. Length into area of a solenoid. Now what is the equation for this? V is mu naught L into A. The value expression will be L into A. Will get cancels. Now the energy density in an inductor, energy density in an inductor will be given by half B square by mu naught. Now this much of magnetic energy density is there. That is energy per unit value. Energy per unit value. That is half of B square mu naught. Half of B square mu naught. Now if I write the equation for how much amount of electrical energy stored in a parallel plate capacitor, that is energy density per unit value in a capacitor, that also I write down here. This is I substitute, I write B, that is magnetic. This is the energy stored in a capacitor. Now this is the energy density of a capacitor, and how much amount of electrical energy stored in a capacitor, that is per unit value half of S naught E square. How much amount of magnetic energy stored in it is the half of B square by mu naught. Now you know that mu naught is a permeability, here permittivity. Now if they are constant, it means that the energy density of magnetic and electrical both are directly proportional to their respective fields. Directly proportional to square of their respective field, square of their respect. This is a very important concept is there. How the magnetic energy density and electrical energy density in inductor and capacitors are related. They are related square of it. Square of it. That's very important question. They might ask you this proportionality here. Now let us move ahead to the next concept, which is mutual inductance. Till now we said the self-inductance, single coil. Now if I go for the mutual inductance, now this is the last concept of this today's class, which is mutual inductance. Mutual induction or inductance. Now here the name clearly says that, let us have an arrangement of two coils. Now this is the what symbol? This is an alternating current symbol in AC voltage symbol. Now let us say this is a primary coil. I have one more coil here. Now this is secondary coil. I have an ammeter here. How much of current is recorded here? Now if I1 is the current flowing in the primary, and whatever flux is given, that is called IP, current flowing in a primary coil. Now whatever flux will be generated here, that is written as IS, means it is a flux linked with the secondary coil. Secondary coil. Here IP is what? Current flowing in a primary coil. Current flowing in a primary coil. Primary coil. Now what I am doing? I am using a variable current. When a variable current flows in a primary coil, if a secondary coil is kept very near to it, there will be definitely flux will change here. The flux linked with the secondary coil will be changed. Now how it is changing? Because when a current in a primary coil is changing with respect to time, it will develop a changing flux here in this. Now how will I write? Already self-evident is that the flux induced will be directly proportional to current flowing through the coil. Here the flux is linked to the secondary coil is changing when a current is flowing in a primary coil. That's why I will write down like this. The flux linked with the secondary coil is directly proportional to current flowing in a primary coil. Current flowing in a primary coil. Now, if I equate, I got an constant of proportionality. I'll write M. This constant of proportionality is called as M is called as coefficient or simply coefficient of mutual inductance. Mutual inductance. This might have been clear here. If M is a constant of proportionality, this constant of proportionality is called as coefficient of mutual inductance. Let us say that if IP value is 1, the current in a primary coil is 1 ampere, the flux linked with the secondary coil is equal to mutual inductance. As I derived in there, I will define the concept in the self-inductance. Now, how can we define the definition of mutual inductance? Mutual inductance, it is a phenomena in which induction of the EMF or induction in the secondary coil when a current in the nearby coil is changing. Current in the nearby coil is changing. If I want to literally define, once again I repeat, mutual inductance is a phenomena. It is a phenomena in which induced EMF in a secondary coil or another coil with respect to changing current in a nearby coil. Changing current in a nearby coil. This is the first definition. Now, if I write if I want to define one more way mutual inductance, how can we define the mutual inductance in a coil, in a secondary coil, is or mutual inductance is numerically equal to flux linked in the secondary coil when a unit current flows in a primary coil. When a unit current flows in a primary coil, in this way also we can define, if a current flowing in a primary coil is a unit current, the flux linked with the secondary coil is numerically equal to mutual inductance. Mutual inductance. Now, this is one definition. If I further go, as per the Faraday's law, what is Faraday's law says that minus L into di by dt, dip by dt. Real or rhythm, it will come what? I will write down here minus d phi d by dt, that is change in flux. Faraday's law says that. Now, what is the phi m? M into ip. If I substitute, it will become m dip by dt. Dip by dt. Now, this is the induced EMF. Here the flux link. Now, how much amount of induced EMF in a secondary coil? I can write minus m into dp by dt in the primary rate of current flowing in a primary coil. Rate of current flowing in a primary coil. Now, if this rate of flowing in a current is 1, once again the induced EMF in a secondary coil is numerically equal to what? Mutual inductance. Once again, we have three definitions for, as we have in a self-inductance, we also have for mutual inductance also will get three definitions. One is very simplified by this. The mutual inductance is numerically equal to induced EMF in a secondary coil when the rate of current flow is 1 ampere per second in a primary coil. 1 ampere per second in a primary coil. Okay. Now, one more last part is that once we have, now what should be the SI unit? The SI unit of mutual inductance is also same as self-inductance. That is, the SI unit of mutual inductance is, Henry. Again, Weber per ampere. Again, 1 volt second per ampere. 1 volt second per ampere. Now, this matter will understand that the definitions of mutual inductance. First one, by method, that is a phenomena of induced EMF in a one coil due to current flowing in a nearby coil. Rate of current flowing in a nearby coil. Now next will be this, the mutual inductance is numerically equal to flux linked with the secondary coil when a unit current flows in a primary coil. Now these three definitions you can understand. Now we will go to the derivation, which is derived expression for coefficient of mutual inductance in a solenoid. What kind of solenoid? Coaxial. Okay, students, let us derive the coefficient of mutual inductance for coaxial solenoids. Here I have considered two solenoids which are rotated on one another. Okay, here I have an air core solenoid. The first solenoid says the current I1 is flow. That's why the name of first solenoid is given here is S1. Okay, the second solenoid is wounded on the first solenoid because both are having a common axis. That's why it's called as coaxial solenoid. Now let us tell about some consideration about here. Let's say S1 is the first solenoid which is having area A1, and N1 is the total number of turns in a first solenoid which is having length L. Now let us have the second solenoid which is having S2, I have indicated here, and there are N2 number of turns are there, which is wounded on the same axis as S1. Okay, his area is A2. Let us assume that the area of the first solenoid is equal to the area of second solenoid. That's why both are having common area of cross section. That's why I written as A here. Now again, both the solenoids having same length L. That's why it is written here. The length of both the solenoid is L. Now this is the first consideration I told about you. Okay, now let us consider that. What are the number of turns per unit length in the first solenoid and the second solenoid? Now in the first solenoid, the number of turns per unit length, say N1 is the number of turns per unit length, that is given by total number of turns divided by length of solenoid. Total number of turns divided by length of solenoid will give you how many number of turns per unit length in a first solenoid. Similarly, how many in S2 solenoid, how many number of turns per unit length are there? That is total number of turns in the second solenoid divided by the length of solenoid. It will give me what is number of turns per one unit length, how many number of turns are there in each solenoid. That will be understood now. Now let us move on to the, if I consider that if current I1 flows in the first solenoid, let us say that let current I1 flows in first solenoid in S1 solenoid. Now what happens? When a current flows in a first solenoid, now current starts flowing in a solenoid, what happens? The magnetic field will generate in which coil? In the first coil, because current is flowing in a first coil. That's why the magnetic field will be generated in a first coil. It means when a current I1 flows in a first solenoid, the magnetic field will be produced in the first solenoid, and that magnetic field will be represented by, let us say, B1 is a magnetic field produced in a first solenoid due to flow of current in a first solenoid. Flow of current in a first solenoid is, as you know that the magnetic field produced in a first solenoid is given by mu naught number of turns per unit length in the first solenoid and current flowing in the first solenoid. Now you might have understand this equation. I will once again watch here. When a current flowing in a first solenoid, you know that a magnetic flux, magnetic field will produce in a first solenoid. Now that is written by this. Now, what will happen to the second solenoid? If the magnetic field produced in the first solenoid, definitely what happens? There will be some magnetic flux will be linked with the second solenoid because magnetic flux will be there flowing. Okay, the magnetic flux linked with the second solenoid. The magnetic flux linked with the second solenoid due to flow of current in first solenoid. Due to flow of current in a first solenoid, there will be a magnetic field produced. Due to this magnetic field, a magnetic flux will link with the second solenoid. The magnetic flux linked with each turn of the second solenoid is given by each turn I am talking about. On single turn I am talking about. If each turn if you go, that will be V1A. If there are how much amount of magnetic flux linked with the entire second solenoid. How to calculate? If you multiply, what are the total number of turns are there? This is for single turn. If you want to calculate the total flux linked to the solenoid, second solenoid, due to current flow in the first solenoid, therefore the total flux linked with the second solenoid, which is having n2 number of turns, this is n2 b1a, Now you substitute the value of n2 here, sir. The total number of turns is equal to what? Number of turns per unit length in a second solenoid into length of solenoid will give you total number of turns in a second solenoid. I'll substitute that one, where the magnetic field produced in the first solenoid is written here. Substitute and I will get the flux linked with the second solenoid will be given by N2L, where V1 is mu naught N1 I1 into A, because area is common for both. That's why I not mentioned here. Okay, now this is the right equation number 1. Now, according to the definition of the mutual inductance, now if you write the mutual inductance, notice says that the flux linked with the second solenoid is directly proportional to current flowing in the first solenoid. What the definition says that whatever amount of flux is generated in a second solenoid is directly proportional to current flowing in the first solenoid. It means that if I write an equating equation, there will be a constant will come. That constant I write it as a M12 I1. And let us say that the current flowing in first solenoid is directly proportional to magnetic flux linked with the second solenoid. That's why it is substituted. It's a 2 is written. Here 1 is written. Now what I think, it is a constant of proportionality. I written is substitute 1 and 2. What it indicates? The mutual inductance of second solenoid with respect to first solenoid. It means, it is clearly says that whatever amount of mutual inductance is generated in second solenoid is with respect to the first solenoid. That's why I written here subscript. It means, what is this M1 constant represents? It is mutual inductance of S2 solenoid with respect to S1 solenoid. It means whatever current is flows in the first solenoid, it generates a flux. Due to this, what happens? There is a mutual inductance is generated. Now, this I write it as equation number 2. Now you compare the equation number 1 and 2, because as per the definition of mutual inductance, it is for your definition of your what is the magnetic field we produce, how many number of flux is linked with that. Now comparing equation 1 and 2, what will get? M12 I1 is equals to N1 N2 mu naught LA into I1. Now I1 is here also, current will get cancelled. What is that meaning? M12 is equals to N1 N2 mu naught L into A. Now this is the amount of mutual inductance we produce in a second coil with respect to second solenoid with respect to first solenoid. Now if you assume, let us assume that let I2 is a current flowing in the second solenoid. I2 is a current flowing in a second solenoid. What will happen? Once again the magnetic field will produce in a second solenoid. Now this magnetic field will generate a flux in a first solenoid. What is the first condition I am telling you? The first condition, when current I flows in a first solenoid, magnetic field will produce. Due to this magnetic field, the flux linked to the second solenoid will change. That is written, whatever amount of flux is coming for one coil, total number of solenoid. I got this one. According to mutual induction definition, I got this one. I have this. whatever amount of mutual inductance will be developed in a second solenoid with respect to first solenoid will be written here. Now I want to know that if a current flowing in a second solenoid, not in first solenoid, if a current I2 flows in a second solenoid, what will happen? There will be once again magnetic field will develop. Now that says that I2 is a current flow. Due to flow of I2 current in S2, magnetic field will come, that is V2 is equals to mu naught N2 I2. Then what will happen? Here become what? Phi 1, that is flux linked with the first solenoid. For a single turn will become V2 A1. Then the flux linked with the first solenoid will be phi 1 N1, total number of turns in a first solenoid. Total number of turns in a first solenoid B2A. Now substitute once again, I will get the same equation. Let us proceed to the actual second case. First case we understand whatever amount of mutual inductance will produce in a second solenoid with respect to first solenoid will be this one. Now let us go to the second case where whatever amount of, I'll just substitute a change here. Let us say that I2 current flows in a S2 solenoid. What will happen? Due to this current, what happen? Magnetic field will produce. That magnetic field I write it down as a, just change the substitute. B2 is a magnetic field produced in a second solenoid when current I2 flows in a second solenoid, that is N2 I2. Now what will happen here? Just change the substitute, it becomes B2 is very easy, it is, now it is here. Now what will happen here? Substitute, get interchange, N1 B2A, N1 B2A. Now this is what happened, this is becomes N1L, this becomes N2 I2. Now what will happen here? Phi 1, and here it will change. It is with reverse. What is the reverse here? Mutual inductance of solenoid 1 with respect to 2 solenoid. It means mutual inductance of S1 solenoid with respect to ES2. Just change the substitutes. Every equation is same. Once again compare equation. I will write it down equation number 3 and 4 here. 1 and 2 is 1. It is very easy to remember if you just change this subscript. Understand, students? Now here what I do? Just the same circuits. 2 1, it becomes 2. The once again remains same here. Now what happens? Once again I got the same equation. It means that the mutual inductance for second solenoid with respect to 1 is equals to the mutual inductance in a first solenoid with respect to second. Both equations are same. That's why simply we write as mutual inductance. Simply we write as mutual inductance. Everybody understand that? If it is asked for 5 marks, you have to derive for both the cases. For the both cases, the current flows in the first solenoid. Whatever amount of flux with linked with the second solenoid will come, you have to derive till M12. Okay. Second case also have to derive the same process. It is very easy for you. If it is for 3 marks, just derive for the first case. Second case, you write it similarly. Current flows in I2 will develop a flux mutual inductance, that is N2, that is also same value if you write. If it is for 5 marks, you have both the cases. This one case is very easy. First, understand what is the magnetic field, what is the flux linked with the firm coil, what is the flux linked with the total number complete solenoid. That is very easy. You might have been understand this. How to derive an expression for coefficient of mutual inductance for coaxial solenoid. For coaxial solenoid means where the two solenoids are rotated on the same axis. You might have been understand. Now let us write about on what factors the mutual inductance is dependent. On what are the factors the mutual inductance will be dependent. Just note down these things. It is a conclusion is there. Now I will write down the factors on which the mutual inductance is dependent. Factors depends mutual inductance dependent factors. Mutual inductance depend on, I will write down the complete word, factors affects mutual inductance. What are the factors which affects the mutual inductance? First one will be geometry of your coil. Geometry of coils. Now see that what are the factors that affects the mutual inductance. Now the first factor is geometry of coil. What is the geometry? What is the size? What is the shape? Because geometry means what? Size and shape. If size and shape changes, definitely the mutual inductance changes. Because if I write the expression for mutual inductance for you, what is the expression for mutual inductance? Simply N1, N2, number of turns in a first solenoid per unit length, number of turns per unit length in second solenoid. Now what is the factor this? This is the factor, size and shape will change here. mu naught is what? Permittivity. Here I have air core. That's what it means. Medium between the core. Medium between the core. This is very important factor. What are the core medium? If the core medium changes, if I own this on a soft iron core, then definitely what happens? My equation becomes what here? If I have m dash, this is remains same. It will mr into m. What is this mr? Permeability of the iron core material. This is what? Mutual inductance of air core. Mutual inductance of air core material. Now this you understand is very important for to know. If I owned it coil on a soft iron core material or any other material which is having relative permeability of value of this one, mu r, permeability of material. Whatever material is selected, they will be given you what are the material of the permeabilities. That means what medium you owned the coil. Now, relative distance between the coils. Now that's one most important thing. Now here see that relative distance between the coil. Now I have two coils. One coil I kept it like this, say S1 solenoid. One more I kept it like this, very close. If I arrange one more thing, see here in these two arrangements, the first two coils are kept a little bit closer, whereas second two set of coils are kept far distance. It means what happens? The magnetic flux will be changing its value. Now how the magnetic flux will produce on a coil like this will be produced. If it is close, definitely value of mutual inductance will change. If the distance between these two increases, it will not induce on the second. The mutual inductance will not generate if the relative distance is increased. That's why the relative distance, if you increase the coil, the mutual inductance reduces. If you reduce, maybe increases. This you understand? Relative distance between the coils. And the fourth one, position of coils. Now this is very important. Now what are the positions on which we are getting a higher value of mutual inductance? Let us assume that I have a coil now. One coil I kept it like this, say S1 I coil, and one more coil I kept it like this. Now see here, I have this arrangement. This is the position of two coils. If a mutual inductance will produce here, now here what happens? The flux, whatever developing on this will be, it is very difficult to link on S1. if a current I2 flows in a secondary solenoid, the primary solenoid will get very least value. That's why the mutual inductance produced in S1 is very least here, because position is very difficult here. Both are perpendicular to each other now. Whatever flux will flow in like this direction, it may not leak the flux here. That's why if the position of this solenoid is kept in this way, it is very difficult. That's why you will get the minimum value of the mutual inductance. You will get the minimum value of the mutual inductance if I keep in this way. One more way is there. That is just now we did. What is that? I am holding the two coils coaxial. Now here we get the maximum value. I say that magnetic flux will be more line numbers up here. That's why if this is the position, that is a coaxial solenoid position, then you will get the maximum. It means I write it down here. M is maximum value. M is minimum value. M is what? Mutual inductance minimum value. Very minimum, very less value. Here you get the maximum value. See that if the position of coil changes, definitely what happens? Mutual inductance value also changes. Now one more is there, side by side. Two solenoids are kept side by side. Now in these cases, the mutual inductance is value is intermediate. Now these are the four factors that affects the mutual inductance. What are the geometry of the coils? Geometry I told you, length, area, number of turns, medium between the coils, mu naught. Whatever the medium is there, if it is air core, you will got this equation. If it is some other material which having relative permeability, it is mu or then it will be multiplied with that. Definitely what happens? If air core other than other material, then permeability will come. That's why you get the higher value of mutual inductance when the soft iron cores of any other materials will be inserted and put at a coils. Now relative distance, I told you that if the distance increases largely, then suddenly there will be no effect of this style of current flow magnetic field on the second. The mutual inductance may be disappear. Next will be position of the coils. Position. There are these positions you understand. This one you will get the minimum. This one you will get the maximum. This one you will get the intermediate value side by side. When the coils, two coils are kept side by side. When the two coils are kept side on axis side by side. On axis side by. I hope that is all understand for you. Next class we will discuss about the AC generator and the principle work construction working and this one. Okay.